LeetCode 28. Find the index of the first occurrence in a string isn't just about locating a word inside another. It mirrors real-world tools like text editors, search engines, and bioinformatics systems, where pinpointing patterns in massive data is critical. Whether you're parsing logs or scanning DNA, speed matters. A brute force search might survive on small inputs, but once that haystack hits 10,000 characters, it's time to dodge a performance disaster. Let's unpack why smarter matching is worth the effort. Let's kick things off with the classic brute force strategy. It's simple to code. Just slide the needle across every possible spot in the haystack and compare. First up, we'll stash the lengths of both haystack and needle. That helps define our window size and keeps things clean. Now we scan the haystack using a window exactly the size of the needle. This keeps our loop from overshooting the edge. Inside the loop, we track how many characters match between the needle and the current window using a pointer. Time to dive deeper. A nested loop compares characters one by one. We keep going while they match, and stop if there's a mismatch or we finish the needle. If our pointer hits the needle's length, we've got a full match. That means we return this starting index right away. But if we exhaust all valid windows without a full match, we return -1. No needle in this haystack. This brute force method runs in big O of n-m plus 1 times m, potentially up to 100 million operations for long strings. Space stays constant at big O of 1. Still, it can slow down badly when patterns almost match but never fully do, a real drag on big data. So how can we trim the fat? Instead of comparing characters right away, we'll use hashes for faster string checks. Enter Rabin-Karp. We begin by grabbing the lengths of the text and pattern, crucial for managing boundaries and skipping impossible cases. If the pattern's longer than the text, we can't possibly match, so we return -1 immediately. Next, we define our hashing setup, base 256 to cover ASCII, and a prime modulus to minimize collisions. We initialize 2 hashes, one for the needle, one for the haystack's current window, and set a multiplier for trimming the first character later on. Before hashing starts, we pre-compute the highest base power modulo our prime. That makes removing the leftmost character efficient. Now we build the initial hash for both the needle and the haystack's first window, one character at a time. We slide across the haystack, comparing hashes first to skip unnecessary substring checks. When the hashes match, we double-check with a character-by-character scan, and if it's valid, we return the match index. As we continue scanning, we update the rolling hash, subtract the outgoing character, add the incoming one, and normalize to avoid negatives. If we make it through the haystack with no match, we return -1 to signal failure. On average, Rabin-Karp runs in big O of n plus m, around 20,000 steps for large inputs. Space stays at big O of 1. Worst case, too many hash collisions can drag it back to big O of n times m. Still, it's a nice balance between brute force and full-on pattern prep. But hash collisions still waste time. For guaranteed linear time, we need a smarter, deterministic approach. Let's switch to KMP. First, check if the pattern's empty. If it is, we're done. An empty string always shows up at index 0. Next, we prep KMP by building a prefix table. It helps us jump ahead when characters stop matching mid-search. We set up 2 pointers, one for scanning the haystack, one for the pattern, so we can walk both in sync. Now we start scanning. As long as we haven't reached the end of the haystack, we compare characters at the current positions. If they match, we move both pointers forward. A full match means we return the starting index right away. When characters don't match, we use the prefix table to skip ahead, as long as we've matched something so far. If there's no partial match, we simply bump the haystack pointer forward and try again. And if we finish scanning without a complete match, we return -1. The pattern's not in the text. Let's rewind and build the prefix table. We initialize it with zeros, then scan the pattern to find the longest prefix that also serves as a suffix. We walk from index 1 onward. If the current character extends a match, we bump up the length and log it in the table. If there's a mismatch after some matches, we fall back to the previous prefix. A smart way to handle overlapping patterns. No match at all? We record 0 and move on. After processing the whole pattern, we return this prefix table, ready to guide the main search. KMP runs in big O of n plus m, still about 20,000 steps for max size inputs. It uses big O of m space for the prefix table. But it never backtracks the haystack, making it both fast and reliable, perfect for interviews or real-world search tools. We started with brute force, simple but slow when patterns repeat. Rabin-Karp gave us faster average performance by hashing, but it still stumbled on collisions. The real breakthrough? KMP. It skips redundant comparisons by pre-processing the pattern itself, locking in true linear time even in worst cases. That's not just theory. It powers real-time search, compilers, and stream processors. In interviews, KMP is a Quack-typical advantage, so here's your next challenge. Where else can you use prefix skipping to make your code smarter? Keep building, keep optimizing, and keep swimming forward.